My article was about the nickel catalyzed aeroboration of cyclopentene. We'll start off with the reagents and the starting material. So first, um, the first reagent that was used was the bisphenol diboron. It was received in a slight excess because during the aeroboration process in the reaction, there is the formation of the aryl ester, um, which comes from the borylation of the aryl bromide, and basically to counteract that, they used a slight excess in the beginning. So when it was first received, the lab did a recrystallization. It was a pretty standard recrystallization, and they followed the following procedure. They used a 2-liter Erlenmeyer flask. It had a magnetic stir bar. They then poured in 100 grams of the bisphenol diboron, and then they added 700 milliliters of pentane. The flask was then stirred in a 50 degrees Celsius water bath, to which basically caused the solvent to start to boil. Then additional pentane was added until all of the solids were dissolved, and then the final volume of the solution came up to 900 milliliters. The solution was then allowed to cool to room temperature, and that was when the crystallization was observed. The flask was then sealed and then placed in a negative 20 degrees Celsius freezer for 2 hours. Then the crystals were collected using the standard vacuum filtration method, and then the crystals were transferred to a 1-liter round bottom flask and dried at zero point 0.3 millimeters of mercury for 3 hours. Um, Then another reagent that was used was the 1-bromo-4-chlorobenzene, and it was also received in slight access because of the same reason, the aryl boration process. Um, and yeah, so an excess was used to counteract that as well. Then terahydrofuran was used, THF for short, and it was collected in an oven dried 250 milliliter Schlenk flask. And basically, it had an argon atmosphere, and then it was also evacuated um, with backfill cycles from a dry solvent system. So that was just to prevent any water um, or oxygen being present in the THF. And these are some other reagents that were also being used. So it's the nickel dichloride, um, the dimethoxyethane adduct, and then the dimethylacetamide, the cyclopentene. That was also the limiting reagent. The hydrochloric acid, diethyl ether, potassium hydroxide, and that was used because of the washing with the aqueous potassium hydroxide removed the aryl ester side product, as well as the excess bisphenol diboron during the aeroboration process. Then we also use magnesium sulfate, hexanes, and silica gel. So a few safety hazards. Actually, for this entire procedure, there weren't any particular safety precautions that were necessary. They did provide a link to a standard lab safety guide. Basically, um, there weren't any procedures that we're unfamiliar with. Everything needs to stay under the hood. Lab safety attire is necessary, goggles, all of that, but nothing in particular pertaining to any of these reagents that were used or processes that were used. And then we can move on to the glassware that was used in the experiment. So first piece of glassware that was used was the 3-necked round bottom flask. This one is a 500 milliliter flask. It has 24 by 40 ground glass joints. This was in the experiment considered flask A. and it's equipped with a metal magnetic stir bar. So on each of the necks, there are certain attachments that are attached. So as you can see on this neck right here, this is where there is a rubber stopper attached. And then the middle one has a glass stopper attached. And then the last one has a vacuum adapter with a stopcock that's connected to a bubbler. You can't see it very well in this image, but it'll come up in the next view. And then the next flask is the Schlenk flask that was used. So this was a 50 milliliter flask. It has a 14 by 20 joint. And this was also considered flask B in the experiment. As you can see here, it's also equipped with a rubber septum and then also a vacuum adapter with a stopcock. And then other glassware that was used in the experiment, these are pretty standard. That's why they're all on this one slide. A separatory funnel, we're all familiar with, chromatography column, and a Buchner flask for vacuum filtration. So now for the procedure. So starting off, they had to prepare flask A first. So there was a great deal of preparation for the environment that the reaction was supposed to take place in. So the first thing they did was that they evacuated it in a 0.3 millimeters of mercury environment. That's the air pressure, by the way. It was flame dried and then cooled to room temperature under vacuum conditions. So the flame drying process is used to remove any water from the flask environment. Then the flask is backfilled with a nitrogen atmosphere, and that is to prevent any oxygen being present from the reaction environment as well. And then flask A is then, after the environment preparation is done, flask A is filled with the bis pinnacolato diboron, and that would be 12.7 grams of it. It had a two equivalents, and it's 50 millimoles. And then it was also filled with the 1-bromo-4 chlorobenzene, about 7.18 grams, and then sodium tert butoxide, 3.60 grams. And then the flask is purged. After those are added, the flask is then purged again with a nitrogen atmosphere by 3 evacuation backfill cycles. And basically that means they cycled nitrogen atmosphere into the flask A to maintain the oxygen-free atmosphere after we added the 3 previous reagents. Then after that, anhydrous THF is added using a syringe, about 225 milliliters. And then the suspension is stirred in a 30 degrees Celsius water bath for 30 minutes. The THF was added while the solids were being stirred to minimize the amount of insoluble material that sticks to the walls of the flask. Then flask B preparation. So similarly to flask A, the Schlenk flask, here flask B, is evacuated also at 0.3 millimeters of mercury and flame dried. Flask B is then cooled to room temperature under vacuum conditions and backfilled with a nitrogen atmosphere. And again, this is to maintain the water and oxygen-free conditions for the reaction to occur. After the environment is prepped in flask B is then filled with nickel dichloride. It'll be filled with about 286 milligrams of nickel dichloride. After that, flask A is purged with a nitrogen atmosphere by 3 evacuation backfill cycles, again to maintain the oxygen-free atmosphere after we added the nickel dichloride. Then the dimethyl acetamide is added via syringe, 26 milliliters to flask B, and then flask B is swirled to completely dissolve the nickel dichloride. And then after that, basically the cyclopentene, 2.2 milliliters, was added to flask A, and then the catalyst solution that was formed just now in flask B is then added to flask A. They're both added to flask A via syringe, and the stopcock on the vacuum adapter on flask A is then closed, and a nitrogen inlet is connected to a Schlenk line and a bubbler, and then that is all inserted into the rubber septum. The suspension turns a purple color after these additions, and the suspension is now set to stir at 30 degrees Celsius for 24 hours. So as you can see here, this red circle is highlighting where the nitrogen inlet is inserted into the rubber septum, and you can see the nitrogen inlet is connected to this Schlenk line, and maybe you can't see it that well here, but there is a bubbler attached. The purpose of the bubbler and Schlenk line is to allow for the nitrogen to be circulated into the flask A setup without allowing oxygen in. So after that, it had turned purple. Then they set it aside for 24 hours. After 24 hours, the suspension took on a light pink color. The reaction mixture is then transferred to a separatory funnel containing 1 mole of hydrochloric acid, 200 milliliters. Diethyl ether, 50 ml about, is used to rinse flask A, and the ether is added to the separatory funnel as well. The funnel is then sealed and shaken. The aqueous layer is then separated from the organic layer. The aqueous layer is extracted with diethyl ether. The organic extracts are then combined in the 1,000 milliliter Erlenmeyer flask. Aqueous layer is then discarded. The separatory process is then repeated again. The organic layer in the Erlenmeyer flask is returned to the separatory funnel and washed with 1 mole of potassium hydroxide. The organic layer is once again transferred to the 1,000 milliliter Erlenmeyer flask. Diethyl ether is used to rinse, and the aqueous layer is then discarded. The organic layer is then dried over magnesium sulfate, and about 15 grams of magnesium sulfate. And then after that, there is a filtration and rotary evaporation step. So after the drying process, the organic layer is then gravity filtered through filter paper into a 1,000 milliliter round bottom flask and rinsed with diethyl ether again, 50 milliliters twice. Then the solvent is removed under reduced pressure using the rotary evaporation. So basically, the solvent that was used during the previous processes was removed using this rotary evaporation machine right here, as you can see. And the settings on that was 10 millimeters of mercury. The water bath temperature was about 30 degrees Celsius, and it was further dried at 0.3 milliliters of mercury for 1 hour to finally attain the crude mixture, which was a yellow oil. Then there was a column chromatography purification step. So the crude mixture is then purified using silica gel flash column chromatography. They used hexanes and diethyl ether as the eluent. The product containing fractions were transferred to a 1 liter round bottom flask and concentrated using the rotary evaporation once again. Settings on that were 10 millimeters of mercury, water bath, 30 degrees Celsius. Then the resulting oil is transferred to a pre-weighed 20 milliliter vial that you can see right here. The flask is then rinsed with diethyl ether again to ensure quantitative transfer. Then the contents of the vial once again undergo rotary evaporation again, same settings, and the product is dried at 0.3 millimeters of mercury for 4 hours to yield finally the 6.67 grams as an air and moisture stable white solid. So it's an 87% yield. So this was the actual column chromatography, like detailed step. So what exactly happened was that the crude product was loaded onto the column, which was packed with silica gel, and slurried in hexanes. So the hexane, 5 milliliters, was used to rinse the flask that contained the crude mixture, and then loaded into the column. The column is 9 centimeters in diameter with 300 grams of silica added as a slurry in hexanes, and then the column was eluated with 200 milliliters of hexanes, followed by 200 milliliters of a 20 to 1 hexane to diethyl ether mixture. And at this point, 25 milliliter fractions were collected while continuing to eluate with a 20 to 1 hexane diethyl ethyl solvent mixture. So the product was contained in fractions 31 to 62. And that's basically the important part here, that's where the product actually appeared after the column chromatography purification. So analysis. So they first did a TLC analysis, and then it was used. TLC was performed using a silica gel 60F254 TLC plate with 20 to 1 hexanes diethyl ether as the eluent. So in lane A, they used the crude reaction mixture before the chromatography, and then lane B, they did the product after column chromatography. So as you can see here, this TLC plate right here, this is shown under UV. It's really difficult to see, but I highlighted with the red circle the spots where you could see it. So on lane A, you can see 2 spots, one up there and one a little bit lower. And then on lane B, you only see 1 spot right here. They also, so the RF value was 0.29, and then they also stained this TLC plate so you could see the circles better. And they stained it with KMNO4, and then so this mark right here on the UV lane A, this is understood to be the aryl bromide, so it's not staining with the KMNO4. That's why you can't see it clearly on this one. But the aryl bromide stain does not exist on lane B, so that means that indicates that the product is pretty pure. It has no solvent in it, no aryl bromide, so that's good. And then the proof of purity, so they underwent a series of NMR. So this was the hydrogen, the HNMR. As you can see, this was the results. And of course, this is the product that we are looking for, the end product. And they also did a carbon NMR right here. And you can see the peaks are aligning. And then they also did a boron NMR, which indicates, if your product has the boron, and it shows right here. And then they also calculated the purity using the HNMR, and the purity was found to be 97%. So this is the discussion portion. So now we can discuss the mechanism that this reaction involves. So before we get into the specific mechanism, generally speaking, this reaction involves the insertion of a nickel catalyst into the carbon-carbon double bond of cyclopentene. You'll see it clearly in the next slide, and then it's followed by the addition of an aryl boronic acid to form a new carbon-carbon bond between the cyclopentene and the aryl group. The reaction process proceeds through a number of steps, including oxidative addition of the aryl boronic acid to the nickel catalyst, the insertion of the nickel catalyst into the cyclopentene double bond, transmetallation of the aryl group from the nickel catalyst to the cyclopentene, and then the reductive elimination of the aryl cyclopentene product. So this is the catalytic cycle that the reaction undergoes. Basically, this the boron reagent basically adds into um, the double bond of the pentene. Um, and you'll actually see it better in the next slide over here. So this is the ChemDraw um, um, reaction right here. This is what it's supposed to look like at the end. This is the end product. So first you start off with the 1-bromo-4-chlorobenzene and basically reacted with the nickel dichloride and basically, and that over THF. And the nickel basically inserts itself between the double bond of the benzene ring and the bromine. And that would be the oxidative addition step. Then you get this compound. Nickel is, as I said before, between the double bonded carbon and the bromide. And this is the point where the pentene is added. The nickel basically attacks over here to one of the end carbons of the pentene carbon-carbon bond, carbon-carbon double bond, and then the bisphenol diboron attacks on the other side of the carbon-carbon double bond on the pentene. And this is insertion as well as the transmetallation that we talked about all in one step. And this is the second step, and it would be the reductive elimination step. So basically, this involves the nickel leaving, taking the bromine with it. So the nickel and bromine combo leave, and we're left with this product right here. So now we can move on to the checking process. So this experiment yielded 6.67 grams of product, and it was an 87% yield, and it was yielded as an air and moisture stable white solid. So they did repeat this experiment, and they ended up like on a identical scale, and they ended up yielding 6.51 grams of the product, which was an 85% yield of, and it was an identical product to the one previously performed. Speaking of repeatability, I do think that honestly, this procedure and this experiment could be repeated in our lab if we had the proper glassware and tools that were used. I think that we could definitely have recreated this experiment, though it would be a pretty long lab because there's a number of different processes involved. But it, I believe, could have been recreated if we were given the proper tools and reagents and uh, machines necessary. These are the authors that were responsible for this organic synthesis experiment. One was Stephen R. Sardini. He's a PhD. His PhD thesis focused on the development of metal catalyzed aeroboration reactions. Um, he graduated with his PhD and began an NIH funded postdoctoral fellowship in Professor Brian Stoltz's lab at Caltech. Then there's Kevin Brown. He began his postdoctoral fellowship in laboratories of E.J. Corey at Harvard University, and he began his independent career at Indiana University as an assistant professor and was promoted to associate professor in 2016. And then there's Ray Turo. He joined the Reisman lab in 2018 to develop asymmetric nickel catalyzed cross-coupling reactions and study their mechanism.